Okay, we're going to talk about divergent plate boundaries now. So here we have all of the plate boundaries, or the plates that on this side of the Earth. You can see that North American plate is actually pretty good, goes right through Iceland. We're going to talk about that later. There's a little plate here, so there's lots of boundaries in the Caribbean and stuff, and in Mexico. Notice that this plate boundary goes all the way along. That's why California has a lot, and Alaska as well, have a lot of earthquakes and stuff like that. So let's talk about it. So we have what is called the Mid-Atlantic Ridge, and that is the first thing we found. So when we look at it, we can see volcanoes, different volcanoes, and where they are located, and they are along those boundaries. Earthquakes can be found in a lot of those areas. Here's the topography. This is what that mountain range looks like, and then how it moves away from that middle part, and then the age of it. So the older is on the outside, the very young parts of the earth are there along the middle. So new crust is being created here. It is not being created over here. So it moves the continents away. That's how that works. Okay, so a divergent boundary, also called a spreading boundary, is mid-ocean ridge or ridge. So this is kind of what it looks like. It's got a kind of a mountain range there and then a valley in the middle. Seafloor spreading causes the plate to move apart. Magma wells up to fill the gap. The magma cools, adding material to each plate. So you're moving that all the time. It's moving away from that mid-ocean ridge. Okay, and here's another picture of the mid-ocean ridge going through there, and how it has moved Africa and South America, as well as North America. If we look at the topography, we notice that this boundary is marked by topographic high. So it's a high, it's a mountain range. Okay. As a result, this boundary is also called the mid-ocean ridge because it's higher than most. So it's about 15 kilometers wide and about 2 kilometers tall. The small Rift Valley at the top of the ridge, so that's where it's the thinnest, and it's moving up, and then it moves apart, and then magma kind of takes its place. The valley is about, I can't read that, wide and 500 meters deep. Okay, so where would you expect to see thicker sediments within the ocean? It would be near the mid-ocean ridge or farther away from the mid-ocean ridge. So sediment from rivers and whatever are going to be found closer to the continents, where we have rivers and stuff like that depositing those sediments. So the difference in heat flow can also be seen across the ocean. The highest amount of heat flow is at that mid-ocean ridge, and then it's less heat as you get. So the oceanic crust emits less heat as it gets farther away from that topographic high. So the lithosphere is also is thinner here, where magma can come up. So we have the most heat here, and then we have less heat flow as it goes away from the thing. Okay, a side view or cross section, the lithosphere thickens as you move away from the ridge. So it's very thin here, but it gets thicker as it goes farther away. The mid-ocean ridge, due to density, is a ridge due to density. The material at the mid-ocean ridge is less dense than the material farther away. So it's less dense here, and as it cools and as it gets older, it becomes much more dense. So the mid-ocean ridge will sit higher in the asthenosphere than along the abyssal plains. Okay. At the mid-ocean ridge, there are two things that make the material less dense. First of all, the material is hot, and in general, hot materials is less dense than cold materials. The thickness of the lithosphere at the mid-ocean ridge is very thin and is made mostly of oceanic crust materials, with a little bit of mantle material mixed in. So as you get farther away from the ridge, it cools off and the lithosphere thickens. So the increased dense mantle material to the plate weighs it down, and it's much heavier than the continental crust. Pillow lavas is a type of volcanic lava formed when lava erupts underwater or flows into water, causing the outer surface to cool quickly and solidify into round pillow-like shapes. So this is the kind of crust that you would see along that mid-ocean ridge as it separates and lava comes up through the middle. One thing that they found is they have found these things called black smokers. And black smokers are a type of hydrothermal vent in the seafloor, has mineral-rich water and forming chimney-like structures. So we have a lot of, they first discovered these like in the 70s. So, and they are home to many, many different organisms that are only found there in that area. They can be found at some mid-ocean ridges. The water enters fractures in the rock, and then since the magma's close, it heats it up and it dissolves minerals, and then that water cycles back out of the rock and the minerals precipitate out quickly. So they form these different structures. The precipitating minerals is what causes the black color. Many different types of organisms thrive in this region due to the rich mineral deposits. So we'll watch this real short video about black smokers later. So one thing that is found is that the Earth's magnetic field has changed over time. So the magnetic pole moves. So the geographic North Pole stays in the same place, but the magnetic pole moves. So the North Pole is not the magnetic north. And currently it is a rate of 40 kilometers per year. So it's moving pretty quickly. So they're thinking that the magnetic field can also flip or reverse polarity, and that may happen. And if it does, it's gonna mess up a bunch of stuff, but not much we can do about it. So when the lava at the mid-ocean ridge cools, it preserves the magnetic polarity at the time the rock is formed. So we can look at different, and they're kind of along these banded stripes. So where it's normal and then that it reversed in normal and stuff like that. So millions of years ago, it has reversed polarity several times. Ships towed magnemometers to measure magnetism to the floor's crust, and they found these anomalies as they went through it, which is really interesting. Wrong way. Okay, and we'll watch Bill Nye later. Magnetic reversal timescale has been assembled. About 500 to 700,000 years is when they flip. So this is a Cretaceous period. It stayed the same for quite a while, but it is a normal part of our Earth. Okay, and again, this is another picture of the age of the seafloor. This time it has the actual plate boundary. So you can see that it's younger in the middle and gets older as it gets to the outside. So shallow earthquakes happen along these boundaries. You can see in Europe it's actually quite active. So how do plate boundaries form? Tectonic plates pull away from each other, allowing magma from the Earth's mantle to rise and cool, forming new oceanic crust. So tier 1, it pulls away, it's a new rift. Time 2, the wide rift, it's widening and stuff like that. And then now we have a mid-ocean ridge as it moves. Okay, and then this is passive margin, so it's no longer active out here, but this is seismically active there along the mid-ocean ridge. Okay, and here's another picture. You might want to kind of look at that. Okay, continental rifting example is East Africa. The Arabian plate is rifting away from the African plate. And the rifting has progressed to seafloor spreading in the Red Sea and the Gulf of Aden. So here it's starting to move across, and it's like getting pulled apart. But recently, this is a new volcano, or it hasn't been active in a long time, but this volcano happened on November 23rd of this year. And I don't know if you saw that news, but yeah. Okay, but we have a failed rift here in the United States. So the mid-continent rift system is about 1.1 billion years old, and it goes from Lake Superior way down into Oklahoma. And notice it kind of is right here in Nebraska. The ancient geologic rift that formed in central North America when the continent began to pull apart, but ultimately it failed and it never did form a new ocean. So it runs from Oklahoma up to Lake Superior, branches out through Michigan and Alabama. Oops, I'm going the wrong way. Most of the rift is buried today, but its signature can be seen through geophysical data, and it is characterized by thick volcanic and sedimentary rocks. That's pretty cool. But we also have a new Madrid fault line, which is down in Missouri and Arkansas and Tennessee. This is a 240-kilometer fault system. It's about 750 million years old, so it's very old. The New Madrid Fault is a seismically active zone in the central United States that runs through Missouri, Arkansas, Tennessee, Kentucky, and Illinois. It is known for causing the massive 1811 and 1812 earthquakes. And we'll watch a little video about that. While the area is prone to frequent smaller tremors, scientists are concerned about a potential large-scale. So if we had a huge earthquake here, it could affect many, 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 many people. So, all right, gotta go.